Good morning, welcome everyone. So before the progress report talks of the Konkoly Research Assistant Program, I would like to briefly summarize the program itself with a particular focus on the changes since this year. I will have my slides in English, but I will talk in Hungarian, so sorry about it. If you have any question, please contact me or László at any time. We are the program coordinators since this year. Oké, szóval az első demonstrátor program, ugye magyarul demonstrátor programnak hívjuk, 2017-ben indult el, erre már nagyon sokat hallott mindenki. Egészen a tavalyi évig ez úgy nézett ki, hogy 3 különböző felhívás ment ki. Volt egy észlelői, egy numerikus, illetve egy mérnöki felhívás, és akkor az interjúk után a sikeres jelentkezők kaptak egy szerződést októbertől augusztusig, és ugye elkezdtek dolgozni egy kutatási témán, egy intézeti témavezetővel, kaptak belépőkártyát, felkerültek a levelező listákra, és ugye nem csak az volt a cél, hogy bekapcsolódjanak kutatómunkába, hanem az is, hogy az észlelésekbe, illetve egyéb tevékenységekbe is, mint normafány, illetve Piszkéstetőn próbáljanak meg minél jobban bekapcsolódni. Én egyike voltam az első demonstrátoroknak, és mi 6-an kezdtük ezt a programot 2017-ben. Ez idén 20 főre emelkedett, és hát ez volt az egyik fő oka, hogy át kellett gondolni azt, hogy hogyan lehet frissíteni a programot, hogyan lehet adaptálódni sokkal több diákhoz, úgyhogy ezért is lettek ezek a programkoordinátor pozíciók kialakítva, amit Laca, illetve én végzünk, és akkor most azt mutatnám be röviden, hogy mégis mik a fő változások, és pontosan amikor különböző e-maileket írunk, és ahol vannak mindenféle szavak, azok mögött mégis milyen koncepció áll. Ugye maga a demonstrátor program úgy néz ki, a fő különbség, hogy az egész program el lett tolva egy fél évvel, szóval januárban vannak az interjúk szeptember helyett, így a naptári évet követjük le, és nem pedig a szemesztereket, ami elsőre furcsán hangozhat, de valójában egy sokkal kiegyensúlyozottabb menetrendet tesz ez lehetővé, beleértve az interjúkat is, amik ugye így a vizsgaidőszakra esnek, tehát például nem kell a hallgatóknak eljönni a szeptember elejé óráikról. Alapvetően a jelentkezők, idén 26 jelentkezőnk volt, és 3 főcsoportra lehet igazából osztani a jelentkezőket. Vannak azok, akiknek már van témavezetője, és a témavezetőnek van valami pályázat, amiből tudja finanszírozni. Őket valójában nem is interjúvoltuk meg, az a témavezető döntése volt, ők megkapták a szerződésüket. És akkor ugye vannak azok a hallgatók, akiknek van intézeti témavezetője már egy ideje, de nincsen hozzá támogatás, ők jöttek interjúra, viszont ugye minden hallgató kapott egy témalistát az interjúk előtt, és az ő témáik már nem szerepeltek ebbe a témalistába, hiszen az eddigi években ugye az volt, hogy valójában voltak ilyen titkos témák, hogy előre le voltak osztva a lapok bizonyos embereknek, és azért ezt kivettük a rendszerből, úgyhogy ténylegesen azok az új hallgatók, akik ugye a 3. csoportban vannak, akik most szeretnék kezdeni témavezetőkkel és keresnek támogatást a munkájukhoz, ők ténylegesen szabad témák közül tudnak választani. Így végül is csak 14 interjút kellett végigvinni január folyamán, és végül összesen 20 szerződés született erre a 2025-ös évre. Őket nevezzük tehát demonstrátoroknak, vagy angolul research assistantet szoktunk használni. Ugye mi van akkor, hogyha vannak olyan hallgatók, akik a támogatás nélkül is szívesen dolgoznának együtt témavezetőkkel, nekik a felvételi bizottság külön ajánlott témákat, témavezetőket, a felvételi elbeszélgetés és a megmaradt témák alapján, és gyakorlatilag szerintem szinte nélkül...
Igen.
Mi történt? Csak beszél. Szóval szinte kivétel nélkül mindenki élt is ezzel a lehetőséggel, és ezért hoztuk létre a Konkoly hallgató lehetőséget. Lehet, hogy nincs megosztva a képernyő még sem? Ja. Ez nem működik. Jó. A másik irány. Tehát mindenkit Konkoly hallgatónak nevezünk, akinek intézeti témavezetője van és intézetben végez kutatómunkát, és ezeknek az alcsoportja a demonstrátorok, a klasszikus demonstrátorok, akik valamilyen szerződéssel is rendelkeznek. És hát ugye azért is szerettük volna ezeket egy kicsit így külön is kezelni, mert a korábbi években meghirdetett programok, azok kifejezetten a demonstrátorok számára voltak meghirdetve, és ezzel a lehetőséggel valójában ezek a programok, ezek most már minden Konkoly hallgató számára elérhetőek, tehát nem erősítjük ezt a mesterséges gátat a szerződéses és nem szerződéses hallgatók között, és így azoknál, ahol például a programok férőhelyhez kötöttek, nem az élvez előnyt, akinek mondjuk van szerződése, hanem mondjuk egy motivációs levelet kell írni, és annak alapján, a motiváció alapján dől el, hogy mondjuk ki fér be. Szóval, ha bárkinek van hallgatója, akár évközben megjelenik egy hallgatója, aki nem demonstrátor, nyugodtan írjon nekünk, és föl tud kerülni a leglistára, és akkor ezzel már is a programnak a része lesz. Ugye mi is maga ez a program, vagy milyen programokat szervezünk úgy általában a hallgatóknak? Ugye az egész program elején, az első héten, februárban van egy kick-off workshop, aminek az a lényege, hogy a hallgatók összegyűlnek, megismerkednek egymással, egymás témájával. Ugye ez a szorgalmi időszak előtti hét, tehát aki most kezdi a témáját, az ténylegesen el tud kezdeni belemélyedni. Akinek már van témája, ténylegesen tud azon dolgozni, mert még nem kell az egyetemi dolgokkal foglalkozni. Úgyhogy ez egy nagyon sikeres program szokott lenni. A másik az a Demonstrátor hét, vagy Demonstrátor hétvége, hosszú hétvége Piszkéstetőn. Ezt gyakorlatilag egy tavaszi iskolává alakítottuk át, ennek volt egy ilyen jelentkezéses menete, motivációs levillel és így tovább. És így gyakorlatilag nagyon köszönöm még egyszer mindazoknak, akik a szervezésben részt vennek. Egy nagyon nagy szervezői csapat van az egész mögött, majdnem az összes ügyeletes csillagász, illetve volt ügyeletes csillagászok, ahol megtanulják a hallgatók a fotometria, spektroszkópia alapjait, illetve maguknak a piszkési műszerek használatának az alapjait. Erre épült aztán a Seri Bálint által kialakított ilyen észlelő hétvége sorozat, ahol utána dedikáltan egy-egy távcsőre, illetve egy-egy műszerre lehetett fókuszálni és megismerkedni velük. Ugye ennek azért is nagyon örültem ennek a kezdeményezésnek, mert az eredeti kategóriák, amiket bemutattam, azok már nincsenek benne a felhívásban, tehát nincs külön észlelő, numerikus, stb., mert valójában az elmúlt években ez már fenntarthatatlanná vált, viszont ebben a formában próbáljuk azt elősegíteni, hogy mégis legyenek úgymond észlelő demonstrátorok is, csak most már nem így hívjuk őket, illetve ez most már így nem csak a szerződéses hallgatóknak, hanem minden lelkes hallgató számára elérhető. Amik lesznek még, amit még kihagytam, hogy például Lacának volt egy előadás, hogy hogyan tartsuk előadást, ez az OTDK előtt volt például egy ilyen kis felkészülés. Ami még lesz a következő fél évben, vannak könnyedebb programpontok is, mint például szintén a Bálint által szervezett süti verseny, ami jövő héten lesz esedékes, de ezen kívül az őszi fél évben is van egy workshop, egy TDK író workshopot hirdettünk a hallgatóknak, ahol el tudnak kezdeni dolgozni a TDK-ikon, illetve nagyon sokan bizonytalanok még abban, hogy hogyan is kéne felépülni egy TDK, vagy hogy kéne ezt kinézzen, a többiek hogyan dolgoznak, úgyhogy erre lesz itt lehetőségetek, és nagyon szeretném, hogyha még összejönne két beszélgetés előadás is. Az egyik az adatgazdászunkkal, Sódor Ádámmal arról, hogy egy kutatómunka során milyen típusú adatok keletkeznek, és azokat hogyan érdemes tárolni, mert ugye nagyon sok rossz példát láthatunk, úgyhogy aki már a cikkírás felé kacsingat, annak ez egy hasznos program lehet, a másik pedig a Gábor által adott tanácsok, hogy hogyan szelírítsük meg a ChatGPT-t, és hogyan tudjuk egy kicsit azt a saját hasznunkra fordítani. Tehát összefoglalva, januárban mennek le az interjúk, a szerződések februártól decemberig tartanak, kivéve ahol valakinek véget ér a jogviszonya augusztusig, vagy a szeptemberben máshol kezd az egyetemet, PhD-ba kezd, nekik augusztusig tart, és utána szeptemberben ugye vagy egy exit interjú zajlik a jelöltekkel, vagy pedig, ami most is fog történni, a félidős beszámolók. Ezen kívül az október-novemberi időszak során nagyon szeretnénk beszélgetni a témavezetőkkel, hogy az ő oldalukról milyen visszajelzéseket tudunk kapni, mik azok, amiket még tudnánk fejleszteni az ő oldalukról, úgyhogy ez nagyon remélem, hogy majd jól fog alakulni, illetve majd november végén pedig elkezdjük a következő felhívást. Lehet beküldeni ugye ismét témákat, és akkor így a jövő hétre meg lesz hirdetve az új program. Ami ugye most fog történni, ezek a félidős beszámolók, és ez egy azért nagyon érdekes műfaj, mert valójában most, és ezzel, hogy elmozgattuk egy fél évvel az egész programot, két TDK között vagyunk, tehát akinek megvan az, hogy mondjuk valaki mit csinált az előző TDK időszakban, akkor láthatja, hogy addig mi történt, illetve fogjuk majd azt is látni a következő TDK-nál, hogy ki mennyit haladt a mostani pillanathoz képest. De hogy nem csak erről lesz szó, hanem bátorítottuk a hallgatókat arra is, hogy beszéljenek az egyéb munkáikról, minden, ami kötődik egyébként a szakmai dologhoz, hogy sokkal inkább egy ilyen szakmai portfóliót mutassanak be. Itt van felsorolva, hogy ezek alatt miket értettünk. Az előadások angolul és magyarul, vagy angolul vagy magyarul fognak zajlani. A mesterszakosokat kifejezetten bátorítottuk, hogy angolul csinálják, de nem szabtuk meg kötelező módon. És hát ugye a legfiatalabb előadónk másodéves BSC-s, a legidősebb pedig a PhD és az MST között egy ilyen gap year-ben lévő hallgatók, úgyhogy nagyon különböző előadásokat fogunk hallani, úgyhogy legyünk szerintem nagyon támogatóak és motiválóak. Van, akinek lehet, hogy ez lesz az első angol előadása, úgyhogy ez egy gyakorlási lehetőség is a hallgatóknak. 8 perces előadások lesznek, 3 perc kérdésekkel, és utána pedig 1 perc arra, hogy váltsunk. Úgyhogy a program nem igazán változott, egy csere lett itt Ben és Peti között, úgyhogy ezt nem is ragozom túl, felkérem az első előadónkat, Fröhlich Viktóriát, hogy tartsa meg az előadását.
Right. Hi everyone. I'm Fröhlich. Well, kind of third-year master students at the moment. Stayed here for another year before starting on to a new topic. And so the title of the presentation is Dynamical Effects of Massless and Exotic Star Systems, but I would rather give you a little bit of a portfolio of what I've been doing in the last couple of months, which was quite a bit, and I will go into detail basically month by month in a second. We're going to talk about conferences, summer schools, research topics, and I won't even have time to mention amateur astronomy, but you know, I'm around, or just hit me up on an email and we can talk about anything related. So starting off in March, I went to a spring school in Italy, in Bertinoro, which was on the birth of solar systems. And we had a little bit of a workshop with ALMA softwares, ALMA observations, and we listened to a lot of lectures. And there I actually brought a poster and also gave a lightning talk on the research that I've done for previous year's TDK that I'm not going to go into detail on because I think many of you have heard that already a couple of times. And you can actually read this poster here next to room 20 if you would like. Then in April, there was the OTDK, where I managed to grab 2 first prizes for some reason with 2 different topics. One was on disrupting planets around white dwarf stars, which you're going to see me do a little bit more of in the coming years. And then the other one was again the last year's TDK topic. And as just a random extra, I also got awarded the Hope Medal from the Proscientia Society, and I also, on the paper now, have a Proscientia Gold Medal, but I will receive that later in November in my hands. And in May, I went to Berlin for a short research visit. I gave a talk at the Planetenforschung Seminar, which is the exoplanetary research group, and I was invited by Szilárd Csizmadia and also talked a lot with Péter Kleivik, who you might know. And we actually have some ideas for future collaborations. Then I was invited for the first time to give a conference talk, which was very surprising indeed, because the conference was on star formation, stellar feedback, and the ecology of galaxies, which I had nothing to do with. So why was I invited? It was actually because of amateur astronomy. John Bali, who you see here holding my little drawings, is a fond amateur astronomer, and the conference was basically celebrating his life's work, because he was 80 years old at that time. And so Viktória thought, and his students organized the conference for him, and I gave a talk on Hungarian amateur astronomy and how that connects to the professionals' work. And we also did a little bit of a star party with the people at the conference. Unfortunately, the weather was not too great, and Visegrad is very light polluted still, so we couldn't see too much, but it was a lot of fun, and I highly encourage everyone to take part in such things. And then the first real research stuff, we got a paper out with Zsolt and Csaba on rings around minor planets in the solar system. Again, won't go too much into detail, but on this plot you can see some small bodies around which you have rings, and the kind of big result that we got was that if you take into consideration solar radiation pressure, you're going to see these rings rotate around the minor body just like a sunflower, always facing the sun with the major axis of the ring. And yeah, you can read the paper if you want any other details. And then in June, I again did another research visit, this time a little bit longer. I went to Heidelberg to the Max Planck Institute for Astronomy. I gave 2 talks again at group meetings, at Miriam Benesti's group meeting and Mario Floch's group meeting, and I'll just leave this up. I did a lot of networking with friends and colleagues, and there was a lot of people there, and it was amazing. So I highly encourage everyone to visit there. Also, I think a very important remark here is that this was possible because I wrote an email after getting rejected for a summer internship call. So if you're ever, in a position where you're not invited for the actual paid contract, you can still contact anyone at these institutions, and that email can actually go very far. Then in July, I went to a summer school, this time in Albach, which was organized by ESA, and the main project was to design a space mission, for which we had about 10 days, which was really about 5-ish, because we had an excursion and we also had lectures, so on those days we couldn't work on the project. But again, I met a lot of people, and we put together a really, really nice mission that went to visit Ceres, kind of as a follow-up to the Dawn mission. And there were 4 teams and 4 categories that you could win in, and we actually won the best science case for a mission, which I was very proud of, and we even got the little Oscar statue. Back onto research again, and again I will not go into too much detail because of the lack of time, but we got a paper out with Zsolt and Józsi on supernova dynamics in a very interesting binary, where one of the components is a red giant star and the other component is either a neutron star or a black hole. We worked that it's actually a black hole, and we looked at different supernova scenarios, seeing how the eccentricity of the system changes, because what was really intriguing in the system is that it's basically on a circular orbit, so that was kind of hard to reconcile with the supernova models, but in the end we got some nice results, and this is already published in Astrophysical Journal. Then going on to August, and this is going to be more research related. So we handed in 2 papers. One of them is mine in collaboration with Zsolt, which is on the TDK topic, so on the durability of moons of rogue planets. So we model a supernova explosion in a system where the progenitor is orbited by a planet that is orbited by a moon, and we basically see how the dynamics of the system evolved during the supernova explosion, and also follow that up with some tidal heating simulations on the moons to see if they can sustain some subsurface oceans. And we also handed in a paper with Zsolt and Csaba on the Koller-Dávid system and its tidal dynamics and long-term orbital evolution. And we're trying to find scenarios where we can actually reconstruct the current orbital position as well as rotational rate of the system. So these are currently under review. My paper is going to be in ANA. I already got the referee report for that, and Zsolt's paper is going to be in PASP. And then in September, I switched the topic a little bit, still working on mass loss, but I swapped from supernovae to Wolf-Rayet stars. This is basically my new ECUP or TDK project that I have to do. And there are these very intriguing systems where you have a binary star that is highly eccentric, and one of them is a Wolf-Rayet. So it is losing mass basically periodically. So you see this is a James Webb observation, by the way, that every time that the stars are in pericenter, the mass loss rate goes up by a couple of orders of magnitude. And so we want to see how these systems evolve long term. And meanwhile, I also got 2 little side quests. I started working with Szabó and Soma on some spectral modeling of disks around white dwarfs, like before, just matching it up with the observations, and then also F Orionis and EX Orionis stars. And also we have an ongoing Tate collaboration with some French collaborators and the Hungarian team, consisting of Zsolt Sándor, Ágnes and Zsolt, and we're looking at the eccentricity excitation of warm Jupiter systems, because the observations show that warm Jupiters actually have a much higher eccentricity than the average of exoplanets. And so with that, we are basically up to date. I'd like to thank you for your attention. Any questions are welcome, and I'm here for like half an hour more.
One little comment, XORs are EX loopy type stars.
Thanks.
EX or is something completely.
Good.
Any question, comments? I would like to maybe just make a few comments, because I agree very much what you said on if you got a reject from a summer school, you can still apply. Let's say I did the same, and I spent 2 months at ESA, the largest basis of ESA at Aztec, just because of that. So we encourage everyone to do it if you wish.
Yes, especially if you are on the shortlist. If you are on shortlist, yes, they already like you.
Yeah, I was also shortlisted, so yeah. I was in the last 2, and then the other guy got picked. I assumed that it was the slot already, given to him, but it was well worth it. A week of
something else I want to point out, just discuss this with Lars and Robbie, that this was a very nice PhD defense talk that you just gave. Like, how many papers was that? 4?
About, yes.
Yeah. So I guess it's summa cum laude. So just to show that, that's not what we, expect from people. That's something we are happy about, very happy about.
That's why I wanted to comment that please don't be embarrassed. This is not normal. It happens in 50 years or something like that.
And EX story is a pulsating venture. So it's but nothing to do with
mixed it up, right?
Yeah. I think it was like the F Orionis was discovered first.
Yes, and then
they were called,
but still like F Orionis or X.
F Or, and then let's call the other ones XORs.
Yes. Yeah.
Because astronomers.
That's why it's a side quest, It's not my main topic.
Okay, thank you very much again. And our next speaker is Norton Szabó. And I will show you when you have only 2 minutes left, so please be aware.
Is it the last slide?
Is it?
Yes.
Oh no. Don't want to do that.
It will be short.
No. Yeah, the first slide, that's fine. Okay, good. And then...
Now we wait.
Yes, now we wait. And now then we share. That's why we need an additional minute. Oh, wait. No.
I'm waiting.
Because... Alright. Good. The floor is yours.
Thank you. Morning, everyone. I'm Norton Szabó, and I will talk about a lot of things that happened. Not as many as Wiki did, but quite a few. So I have a few supervisors at this point. So some collect Pokemon cards. I do this, and with all of them comes different topics actually. So one of the main things that I was working on are the NEO discoveries, the nearest object discoveries at Piszkéstető. As you know, we use the Schmidt telescope up at Mátra. We started its observing in the 60s with photographic plates. It's really dim, but here you can see that the field of view fully contains the Andromeda galaxy, which was lost after they upgraded to CCD. The field of view shrunk, then it was updated and it grew again a bit, and after 2020 there was another upgrade, and now we have the full, almost the full field of view back. And since then, actually Christian Shanesky discovered quite a few NEOs. There will be a test at the end, so you have to memorize them. These two are partially my discoveries. Okay, so we have almost 300, or Christian will say that we have more than 300, but this is what's officially up there at the Minor Planet Center. So what to do now? Let's make it more efficient. That was the quest. So I started doing some statistical work on what happened previously. For example, in this map, you can see which part of the sky was covered within the first 2 years of this program. As you can see, the galactic plane is avoided, and of course, we have a very small amount of data from the southern sky because it's hard to see from Piszkéstető. And there you can see all the discoveries which are scattered all around. I also looked at what's the best time to observe NEOs. So not only the areas, but what's the best time. And you can see here all of these plateaus that appear yearly, and it turns out when there's no night in the summer, you cannot discover that many NEOs. So there's a clear dip over here, and we can also expect a spike in a few weeks from the discoveries once again. I also wanted to see if there's any, so between observations and between discoveries, how much time passes actually. So I figured out that here you can see the interval, so how many time is spent between each discoveries, and most of the cases it is 1 or 2 days, which is, first of all, it could be interesting, but then you realize that this is because if you have a clear sky, then it is likely that you'll have another one next day. So this is just a weather artifact, actually. I have many other ones of these. We have handed in a paper on this. So we just got the referee review. So now we are working on that. And on this work, I was invited to the Netherlands to the Embassy of Hungary in The Hague to present our work at the first Hungarian scientist meeting in the Netherlands, which was quite an interesting opportunity. So this is almost half of my time was spent on this project and something else. Around the time when we started figuring out it would be better if we did the NEO discoveries more efficiently, József Vinko had an idea that if we did some spectroscopy with meteors, that might be a way to channel some money into our research projects. This idea was born at a conference in Kutna Hora last year, where I presented some of our works at the International Meteor Conference, and it turned out that there's a lot of interest in spectroscopy actually in the meteor world. So we then started building our own spectrograph. We just presented this with a poster last week at the Netherlands at the International Meteor Conference, and I also gave a talk which I wasn't expecting. So I was invited on Tuesday and the talk was on Sunday. So
next Sunday or the previous? Next Sunday or the previous?
The previous, so. Yeah, so we have some preliminary results. We already captured the meteor and we know that it has magnesium and sodium in it, which is nice. And now something else. We also figured that we have all these meteor cameras spread around the country. Let's try build some, and let's go to the source on where and how to build. So I spent my summer in Maryland, in a town called Monkton, next to Baltimore, with Mike Henke over here, who is the developer and the main manufacturer of the All-Sky 7 network. We also try to develop a dark flight model which can predict where each meteorite falls. So after we captured it with the meteor camera, we can predict, okay, they are, so the predictions are here, but actually the meteorite was found here. It's not too bad, just a few hundred meters over. I learned a lot of how to use Cloud and ChatGPT for programming, and I learned a lot about how not to. So we ran into a problem where the AI was suggesting solution A that didn't work, so it was suggesting solution B that didn't work, so it suggested solution A, and we got into a loop. And we read at some forum that if you give some stakes to the project, that might kick the AI to the right direction. So Mike decided to threaten the AI that if it didn't succeed, then a baby lamb would be sacrificed. Which worked, actually, you know, which is surprising. For a while it worked, but after about 1.5 days, it started asking questions about the lamb and how it's going, and it refused to work until we had proof of the live and well-being of the baby lamb. So do not threaten the AI, because now it's just an inconvenience, but in a few years, you know. So we went on. I built some cameras over here. You can see where our plan was to create an off-grid version. So I did some, you know, amazing electrician work over here to make this whole thing actually work. I used a lot of materials for this project. I learned a lot. I also had some amazing time there. I created a 15 episode YouTube vlog series out of my work. So if you know you have 7.5 hours, I might be able to share it with you. So as the end product, let me present you the All-Sky 7 off-grid that we created. I have just finished with the prototype the day before I left the United States, and it's been working for 1.5 months perfectly. So I think it's a great success. Thank you so much.
Questions?
What happened with most of the 170 something kilograms of steel? That was certainly not built in the prototype.
Well, many of us lost during the manufacturing process. So we did some unholy things with the metal that made it impossible to then reuse for next prototypes. So, yeah, it wasn't the most sustainable way maybe to build it, but we had to do it fast because we had a contractor in the name of the United States Department of Defense, and the DoD, you know, they demand, and we had to finish it within the deadline.
Any other questions?
If not, because we have a small delay, let's thank again our speaker and let's the next speaker is Gábor Kreinicker.
Megbocsátok a gépet.
Majd fogok jelezni 2 percnél, és akkor, hogyha már...
Jó, majd igyekszem a végén meghúzni. Nem jön az. Ja.
So, hello everyone, my name is Gábor Kreinicker. This is my last semester at Budapest University of Technology and Economics, and as a space engineering student, and this is my 6th year here at the Astronomical Institute, so I'm here for a while. Yes, and today I will talk about what I was working on in the last year with Andris. So, my work can be split into 2 parts. First, I was working on the infrared sensor calibration. We use these sensors in satellites like GRB Beta, Unity or MRC 100, and we use these sensors to determine the satellite's attitude. So, after we download these 16 by 12 pixels images from the satellites, we post-process, and with image processing we try to determine how the satellite is in space. So this is our work. As you can see, there are 4 images synchronized next to each other. You can see the Earth, and you will see the Sun. These are the 2 objects that we really want to detect, and we calculate their attitude from these data. Here's the Sun. Okay, so first I started with sun detection. It was pretty hard. I thought it will be easy because it's a really bright spot, but no. Unfortunately, it can be split into 2, 3, or 4 pixels. But I made an algorithm that can determine where it is. It works pretty well, as you can see. And also, it is more accurate than the resolution of the sensor. As you can see, the center of the circle is not in the pixel inside, but it determines where the sun can be. But as you can see, there are some fault detection on the top right corner. This is because of the vignetation of the sensors, and this is a huge problem, so we started to calibrate it. I did some pre-calibration last year. We measured the temperature of the sensor itself, and we got some interesting data that the temperature of the side of the satellite can be between -10 and +70 degrees Celsius, and this is really fast, as you can see, so it could be a problem, but fortunately it isn't a problem. as you know that the satellite is working today also. So yeah, so after some failed attempts to do it easily, we try to do the datasheet thing that we remove the vignetation with full calibration. It was really hard. There are a lot of parameters and numbers and tiers before we remove the vignetation effect, but as you can see, this is the image before the calibration and this is after. Ooh. So, as you can see, the vignetation is removed and the Earth and the Sun didn't fainted anything, so I was really happy. So this is a side-by-side comparison, and right now, this is how it works. There are some strange patterns in the image that we didn't know where it comes from, so right now we are trying to find out that why is that pattern here, but it works. So after that, I broke a rocket half in Sweden, but I don't want to talk about. So the second half of my work was to create an S-band receiver antenna in Piszkéstető. These are the clear instructions I got from Andris that we should make an antenna something like that. So he bought a parabolic antenna reflector, and my job was to make a feed, the thing in the focal point that converts the electromagnetic waves into signals. So we wanted to download more data in a wider bandwidth faster, and this is why we wanted an S-band receiver, which is about 2.4 gigahertz. Yes, so first, after we look at some feed types, we choose the fireback helix antenna because it has a wider lobe width than any other feeds. So I made this ugly candy-looking thing that didn't work well. I was able to make it well, but not quite well. As you can see, there are some radio technical parameters. The return loss, which is good if it's way below 0, and the standing wave ratio, which is good when it's really near to 1. And it was quite good, but it wasn't really, so it alternated when it was moved. And it was a bad thing, so I made even more candy-looking thing, which was quite more stable, but it was the worst antenna I ever saw. Even a wooden fence would be better. So I made more prototypes, more candy-looking thing, and better results, but it was bad also, so I made more and more, and it got better and better, but not the best. And then I had a lot of candy, and I was not really happy with the results, and I also made it to the L band, so which is about 1.6, 1.7 gigahertz for us. But at the end, I got this candy, which looks exactly the same like the previous ones, but it is quite good. It has about 1.16 standing wave ratio, and the return loss is over minus 22.5 almost. So it was better. So only one thing were back testing. So we mounted the new feed into the antenna, we make it into the focal point, and we tested it on weather satellites, geostationary weather satellites. These are using the L band, so 1.6, 1.7 gigahertz. We didn't receive any data yet, unfortunately. We thought that it could be because of the radio noise coming from the city, which is quite bad, and that's because we wanted to. We will test it in Piszkéstető, I hope, so it will be a better place for this antenna. Yes. So with these two images I made, not quite good I know, but I made it in the top of the institute, and I really want to thank you for your attention.
At which wavelength is the infrared sensor sensitive?
Mid-infrared.
But how many microns? 5, 10, 15?
I don't really know.
It measures flux. Yes, flux flow, inflow from the sensor, outflow from the sensor. So if you want to convert it to wavelength, it's something like 10-ish microns, but it works a little bit different way. So it's not a kind of imaging sensor that you get used to from astronomy or astronomical detectors. It's completely different. It's
At least comparable to James Webb.
That's some sensors.
Yes,
Just smaller.
And
if something is bright enough like the sun.
Is the detection stuff running on board the satellite or offline?
We want to implement it on board, but right now we do it offline, post-process. Yes.
I have a question.
Well,
You're older than me, so.
About your feeds.
Yes.
What made the difference between the bad ones and the good ones?
I made the connection a bit larger, or the dimensions a bit larger or smaller. So
It's under your control, not a random thing.
no, it's under control, but no one knows how it will behave. So I had to do a lot of prototypes to test how it will behave if I made some dimensions in another way. Yes.
Yeah. Have you tried to correlate the image of the Earth of what you would expect to see? So do you recognize any features on the planet?
Yes, there are warmer spots and cooler spots. It depends on which side of the planet the satellite is looking at, and we can see the clouds also. Yes, it's in low Earth orbit, so we look at a smaller part of the Earth, about 40% maybe the surface of the Earth.
Right.
So it's a very torzított distorted image tech.
Yeah. Cool.
Okay, let's thank a speaker again. And our next one is Julika.
Okay.
Welcome everyone. My topic is actually last year's topic, so I will kind of skim through it because I've presented it quite a few times before. But my topic was about large-scale structure and its correlation with cosmic microwave background radiation, and how we can detect this, or in the future in the observations of the Euclid telescope. If we zoom out from the universe, we can see a web-like structure where each dot is a galaxy, and these huge kind of underdense regions are called cosmic voids. And we are interested in cosmic voids because we expect dark energy to have a stronger effect in them, and so they can help us constrain cosmological parameters. And for Euclid observations, there have been quite a few forecasts, but there hasn't been one that correlated the voids with the cosmic background radiation. So a little bit about the background radiation. We know it comes from the early times of the universe, and we have quite a lot of knowledge about its spectral energy distribution and what kind of small like fluctuations there are in it. And if we know these distributions, then we can measure the differences from these distributions. And one of the secondary anisotropies is weak lensing. There are many other effects, but it basically means that as the radiation, so basically the photons are coming through space, they get affected by the structures that are in space and get gravitationally lensed. So we can see it as the original spherical object getting larger or smaller, I mean its image getting larger or smaller, or it gets distorted. And what we want to measure is how much it gets magnified. This is also called convergence. And there have been quite a few studies where Ágnes was also working on the correlation between voids and background radiation, because we expect that in big galaxy clusters there is some kind of gravitational lensing. So there is a positive convergence of light rays, and in voids we expect some kind of divergence of light rays. So if we correlate the two, there should be some kind of effect there. And so what we have been working with is the Euclid mission, and we are very happy because the first data release will be this fall, internally. Public will be sometime next year. But it is a survey that scans these blue regions, so a huge part of the sky, and very good resolution. So it will be good for cosmological research. And there is also a very detailed simulation for it, which has just become public. If you want to use something, a kind of simulation where you have lots of galaxies and galaxy properties that you can look at. And so how we create a simulation or mock observation for the real observations is we need all kinds of simulations and programs to create, first of all, a universe populated with galaxies. We also need to find these cosmic voids within these galaxies, and then we need the background radiation map and the void map and stack them together, because each void has a really weak signal, so we need to stack them together to get some kind of stronger signal. By the way, this method is basically, I'm following Csilla's work, who was also András's student, so I was heavily relying on that method. And so I created my little universe and compared it to the flagship simulation, and also compared the voids to what we can expect. And it was fairly good. Then I correlated it with the background radiation map, and this is basically what we expect, that in the middle of the voids there is a very negative convergence, and then as we get closer to the edge, it gets higher, and then the effect evens out. And it's very consistent everywhere on the sky, which we are happy about. And we could also look at different types of voids. Some are in denser regions, some are in very underdense regions, and we could identify them. So yes, we can see a correlation. We are happy about it. Of course, there are lots of limitations of simulations, but as data is coming out soon, we can create
comparison with actual observations and see how well we did in simulations. And there was a lot of things going on with this project. I presented at TDK, OTDK. There was also an extragalactic workshop within the institute where I presented it. I also did a poster of it. I wanted to challenge myself because I've done presentations like this before, but the poster was a new thing for me, and I also submitted it as my bachelor's thesis, and Csaba István was my internal consultant who also helped with feedback about my thesis, and yes, some pictures about what happened. I graduated, yay! Yes, those are my parents. And I also did, yes, participated in some research assistant events. I forgot that I also did the spectroscopy observation small training because I was interested in that. Also, I always try to find some kind of summer schools or something related to physics that I can do in the summer. So I did these just from my own volition. And I'm also doing social media for this postdoctoral fellowship program, and Ágnes organized this nice conference that was also really good for networking. And yeah, there are some ideas for the next project, but we're not set yet. Thank you.
Anyone has a question?
A live question. If you look at a given direction, there are many voids, I guess.
Yes.
So I guess it makes a difference whether this void is closer to us or farther away. So how the effect on CMB, to put it another way, what are your voids at what redshift?
They are around 1.3, 1.8. The reason is that this is near the cosmic known, where there's the strongest galaxy formation and light structure formation effect. And actually that is something I was thinking about, is that we could check this effect like at different redshifts. Probably the strongest is around here when there are most of the galaxies forming, and there are some changes as it comes to closer redshift and some extra effects.
What do you expect from the first data release of Euclid?
Lots of work. Lots of work. It's going to be around not 2,000 square degrees, but something around that.
It's shrinking all the time.
Oh, really? Okay. That's. But I think it will involve many people and lots of work, because the concept is like you get an internal data release and you have until the public release to write your papers. And that means that everyone has to help and participate in it. So hopefully I can get a little piece to participate in it.
Okay, thank you very much again. Our next speaker is Ágnes Bogdán.
All right. Hello, everybody. My name is Ágnes Bogdán, and I'm a physics student at ELTE, and my supervisor is Dr. Ágnes. And today I will talk about large-scale structures, more focused on voids. But before jumping into this topic, I quickly want to mention that I did a poster presentation at Bolyai conference. I participated at the extragalactic workshop organized here by Ágnes in the Institute, and I was lucky enough to attend the Dark Map conference organized in Budapest by Ágnes in September. And like a really happy news, I can present that just this week, this paper, which I also contributed to, has been submitted on Monday or Tuesday. So this is a quick recap about the past few months. But now, jumping into the science part, what does a cosmologist do? Rest assured many things, but I want to talk about mapping the cosmic web, the cosmic, like the underlying dark matter skeleton of the universe. So we want to map it. How? It depends on what redshift, but in my case, QSOs, quasars, are really important. So yes, let's map the dark web with quasars. But if we have quasars, is it enough to just know their position to map the dark matter distribution? Not really. Then let's start to find the structures, like like clusters. Quasars group together, bound by gravitational interactions. So we have one type of large-scale structures. The other type are voids, and they are slightly or very different than clusters. So you can imagine that they are large structures with low density, fewer galaxies inside them, and in general they are way larger than clusters. So this is one way to map the dark matter distribution, but I want to step over here. How can we distinguish between two models, let's say? Because you can clearly see that here dark matter distribution is very different than here. So to somehow give a motivation, why am I doing density profiles? Because these profiles can give us a picture about how the dark matter is distributed. So I will come back here and show you quickly that on this plot you can see the comparison of the density profiles of clusters and voids. And so voids, clusters, voids, clusters. Here you see the relative radius, so you can clearly understand that in the center of a cluster the density is pretty high. And as you go outwards, the density drops and it converges to a mean density. What about voids? You see that in the center of the void, essentially, that's the region which is the most underdense. And as you propagate towards the void radius, the density grows, there is a bump, and then it converges back to the mean density. So this is what I did for my TDK and my bachelor thesis. But you can ask the question, okay, but what data are you using? So let's take a step back or two, and I want to talk about the Quasar catalog, the Gaia Quasar catalog. So just to quickly mention things, you know more than me probably that Gaia was not meant to do this, but there were a lot of observations, and actually around 6 million quasar candidates have been found with Gaia. And after cleaning, for example, they made color and proper motion cuts in this initial quasar candidate catalog. They improved the redshift. They put together Gaia and WISE data, and the final product is this Quasar catalog, which I was also using, which contains 1.2 million quasars. It's almost full sky, apart from the galactic plane and other patches on the sky, which are contaminated, let's say. So this is the catalog, or the basic data we've been using. But going beyond my TDK and my bachelor thesis, the important or like the biggest task was to, okay, how do we go from this created method to measure the density profiles of different structures to do it for other or more, like 50 new mock catalogs or 50 new simulations with additional features, many additional features. So I want to walk you through the process or the thinking part about what we did and what are the improvements and the additional features. So one thing we wanted to include is to be able to measure the density profile of different types of voids and clusters. Julia also talked about these voids in underdensities, voids in overdensities, and so on. Another thing which is very important for us, but I don't think I will have time to talk in detail, is about considering the edge effects. Maybe if you have questions, I can answer them. Also, a very important thing was to understand our data. Does our data allow us to really have a good resolution in the center of the voids, or no, or like these questions? And of course, this is technical, but distinguishing between the barycenter and circumcenter of the voids was like a hard topic for us, but understanding it put us closer to find a good method. And here I want to mention that working with Nestor Ardanov and Mark Nessar under the supervision of András, we did a lot of thinking, and not just thinking, but working too. We compared our results, our methods, different methods, same methods. Do we get the same thing? Do we understand how our method works? And if it does what we wanted to do. So we finally arrived to the 50 mock catalogs, and I will talk about what they mean. So these mock catalogs are slightly different simulations with lambda CDM cosmology, but of course they are slightly different, but but statistically they show similar features. So each of these mocks could be our universe in a sense, statistically. So for example, the size of the voids and the clusters, the number of galaxies in them pretty much agree. And I want you to look at this really nice plot made by Nestor. Here you can see the comparison of the void radius distribution in the QIA, the observational data, and the 50 mock catalogs. And you can see that the histograms and the curves follow each other pretty neatly. And now, arriving to the density profiles, here I want to show you how similar the density profiles produced from these mock catalogs look like. Sorry. I'm taking 10% of the voids from each mock catalog and I'm comparing them. So they follow a pretty nice line together. And since my time is up, I'm just gonna leave this very busy plot over here, but here's a little cheat sheet so you can understand it. Here I only wanted to show that so the mock catalogs pretty much agree, very well agree with the real observational data. And one short sentence about the future project. With this tool set, we can analyze different interesting things, because we are able to say a few things about galaxies, not just galaxies considered in their position in a large-scale structure. So if they are in the middle or in the outer skirts, and so on. So thank you for your attention, and I'm happy to answer questions.
May I have a philosophical question? Voids are defined by their walls, the galaxies which surround the void. Yes. What do you think is more important? The lack of galaxies in the void, or the excess of galaxies in the wall, the bubble? bubble hátján.
I think you mean like this bump over there, and I didn't have time to talk too much about future plans, but exploring velocity fields of these structures can really answer the question which are more important, or you can just explore this artifact that the velocity field is different over here than it is here because here are more galaxies, so they are essentially pulling the matter out already.
So I have a really many question on the radius distribution of voids.
Yes?
Isn't it the center around 0? It's centered around some
So this is the effective radius of a void. So it's like, I don't know, 100 megaparsecs. So that's
So it's a characteristic feature for universe, right? The typical size.
yes, I could say that.
I see. Because I would argue
So
that small voids are more abundant.
Can you explore what you mean about that word?
So you have a characteristic typical size of voids, which is larger than 0.
Yeah, and small voids are probably more difficult to detect.
The thing with small voids, with low member galaxies or few member galaxies, you have no resolution to like analyze the density profiles, for example. So that was a difficulty we had to consider, that if there are only 5 galaxies in that void, what do you do with 5 galaxies?
But if you have bubble foam on the water, floating on it, you don't have very tiny bubbles. There is a certain characteristic size of bubbles in the foam, if you think of that. So maybe the voids are more important than the bloody galaxies in the walls. Sure.
Try it in reading that one.
I will certainly try.
Depends on the physics, I guess.
Yeah, or the soap.
Yeah, or the soap. Or the universe.
Okay, thank you very much again. Our next speaker is Bettina Kozák. So hello everyone, my name is Bettina Kozák, and my supervisor is Fröhlich Viktória, and my topic is going to be relativistic jets and how to measure them. Now, unfortunately, it's not as magical as it sounds, but we try to model it or kind of understand what's going on, but we still don't know for sure, so it may be. So just a quick recap on how energy and an active galactic nuclei is structured. It has a supermassive black hole on the inside, on the very center. It has an accretion disk around it and the dusty torus. And also it has a jet perpendicular to the accretion disk, basically. And my topic is around these relativistic jets, because they have relativistic flows, plasma inside of them, that just shoots outside the galaxy. So, but about the jets, we don't really know how they work. So we kind of understand that it is because of the black hole's magnetic fields and the accretion magnetic fields. It conjugates the plasma and kind of shoots it out. But the launching mechanism is questionable about how it works, and the kinematics and the dynamics and the evolution of the whole jet is really in question or in debate. But we have some models, and just to make it harder, there are 2 types of radio jets. So the radio emission can be 2 types, the panel of Rayleigh, type 1 and type 2. With the type 2, I'm going to start with that, we have 2 radio lobes at the very end of the jets and hotspots. This is where most of the radio emission comes from.
This is a little bit easier to model because we can model it with nominal flows, but MHD equations basically. I'm not professional at it now, but the Konkoly type 1 is a little bit harder because we do have turbulent flows in them, really strong magnetic fields. So we still don't know how to model. So we have really the simplest models is the one-zone model for the jet flow. It's basically tells that the emission, all of the emission is coming from one zone inside of the jet. Now this is good because it only has a few parameters that we need to find out, and at the first suggestion it is used. We also have the blob in the jet model where we have multiple blobs in the jet that have some certain speeds, and they are responsible for the most of the SEV emission, and there's an ambient emission from the jet itself. And recently they proposed a new idea, or not recently, but reworked it, this spine sheet jet model, which I think is really interesting because it tells you that there's an inside spine of the jet, which is much more, which has higher speeds. This is the one that has relativistic speeds, and it can accelerate electrons and atomic matter really well. And there's an outer layer, a sheet, where it has much lower velocities. It may not even reach relativistic speeds either. This is important because all of these models have one thing in common, is some parameters. One of them is the Lorentz parameter, which is a really important parameter in the jet, because as you learn it, or will learn it in relativistic courses, it is related to the speed. It is a measure of speed compared to the speed of light, but we have different methods to measure this parameter. So you can see a plot in here where in AGNs, especially in blazars where you see them face on, so you almost look into the jet when you see a blazars. It really depends, the Lorentz factor really depends on the viewing angle and also how fast basically the jet is. And the higher the Lorentz factor, the higher the velocities and smaller the viewing angles are. So different methods can tell you this Lorentz parameter. Basically, one of them is the variable time scales, where you see so blazars are really variable in the electromagnetic spectrum. You see one regime, it's variable, and you kind of predict based on a model that in another regime how much or what's going to be their flux, and you compare it to the measurements, and based on the excess you can somehow tell the Lorentz factor. I'm not professional at this, but you also have just SED modeling, when blazars basically have these two-hump structure in their SED, and they try to model it with leptonic or leptohadronic models, the best fit case. And also we have the LBI, basically radial mapping, when you actually look at the object and you have some components that you see throughout the years and how they move out, you measure their speed, and based on cosmological calculators you can get back their real speed, and from that also with brightness temperatures you can tell the Lorentz factor. Now in my topic we found a paper that used a leptohadronic model to basically tell something other parameter, but we were interested in the Lorentz parameters of these 300 blazars that they have used. And what we wanted to see is how similar our Lorentz factors is to theirs. So if the model is right, then we should kind of get the same Lorentz factors. What we have found out is that it did not. If they give back the same Lorentz factors, then there should be some rough of a line here with some scatter, but as you can see, it's all scattered. But an also important note, if you look at the distribution of the Lorentz factor, we kind of have the same distributions of the Lorentz factor. Statistically, they are not that bad. So the model is not that bad, it's not bad at all. Of course, there can be a lot of reasons why they are different. This is what we're really focusing on. First of all, these objects are really variable, as I've said, so we can have a higher Lorentz factor in a flare state. But we try to give a median value for the Lorentz factor in VLBI, and they try to kind of give it in the model too. Also, there are some things that they don't account for, like external photon fields, only internal photon fields, and in the model they use the one-zone model, and also they started with leptonic models, and then tried to correct for the parts that didn't match the acidity with leptohadronic models. So it's really complicated why it can be the same. So what we have to do now is to look at the model and other methods, how they are compared to the model. So we have two databases. Basically, these are two different papers that they measure the variable Lorentz factor, the variability method. And if we compare them to the model, we see that there are some scattered random spots. But what we are interested in, VLBI, is how they compare. And you can see that the VLBI has some structure if you really look into that. So the question is, why now is why could this be? Now, some events that I have attended throughout the years was the Konkoly Galactic workshop, just like the talkers before me, and I also took part in the Dark Map conference. And I was lucky enough to take part in the JAI VLBI school, where we learned how to use Quasar, why it is better, why it is not so much better. And our future plans is right now with PDK. Thank you for the attention.
Questions?
That scatter plot, one of those, if you go back, that one, go back. No, back, forward. That one. The right-hand side is exactly like the one which is in a meme, a Facebook meme I saw several times, where at least 20 different types of functions are fitted in those. Please check it, you will find it. I'm pretty sure that the point structure is exactly. Maybe it's a hidden relationship, various realities.
You can draw a unicorn into it.
Well, it's a sheep to make them big.
But to have a serious question, the Lorentz factor 10, 20, 30, that means 99.9% speed of light, something like that?
Yes. So really high Lorentz factors have higher errors too. So we kind of are interested in maybe until 30. 50 is really rare and really high. So if this scatters, it's not as much of a concern. Then it scatters here, maybe.
Okay. Do these points have error bars?
Yeah, this is on the list of the typical questions.
They are so small they can be seen.
Right.
Okay, thank you very much. And our last speaker before the first break is David Koller.
Okay, so hi everyone, my name is David Koller. I'm a second-year astronomy master student, and my supervisor is Sándor Frey. First, I would like to share some insights from the findings of my first author article, which was published this spring. After this, some of my other achievements will be presented too. So, during my work, I have created clean maps of the Quasar J1429. These clean maps clearly show multi-component jet structure and a bright and compact core region. The outermost component is located nearly 40 milliards seconds from the core. Given the distance of the source, it corresponds to around 300 parsecs. Another interesting thing is that around 20 milliards seconds, we can observe a significant bending in the jet. After creating clean maps, I modeled the brightness distribution. During the modeling, I fitted circular Gaussian components to the visibility data. Based on this, the core jet distances and the position angles could be determined. At 2 GHz, for the J1 and J2 component, no proper motion was detected. For the J3, however, proper motion was observed, but it can be fitted with a smaller error at 8 GHz. Besides that, as we have already seen, there is a bending of nearly 60 degrees in the jet. This could be due to the interaction of the jet with interstellar gas or a change in the black hole spin axis. Based on the 8 GHz data, 3 apparent proper motions could be detected. These are shown on the slide converted to speed of light units. Furthermore, a recent study suggests that proper motions of jet components in sources with similar redshift typically range from 0.2 to 10 C. So the J3 component is one of the fastest jet features known above Z3. For further calculations, I used the J5 component as the basis because it is the closest to the unresolved inner region of the jet, so it is expected to best represent the innermost segment of the plasma beam. And among the 3 available epochs, only in one case was the core size larger than the minimum resolvable size of the interferometer. So I only provided lower and upper limits for the derived parameters. Based on this, the brightness temperature exceeds the equipartition value by an order of magnitude. The Lorentz factor and Doppler factor and Lorentz factor are above 8.8 and 5.7 respectively, and the inclination angle confirms that the source belongs to the blazar category. So, based on the derived limits, the J14 fits into the known average high redshift radio loud active galactic nuclei population. However, I note that we followed a conservative approach. These values could be much higher if we consider this brightness temperature value obtained from the latest measurement in 2018. But considering the 50% jump in the flux density and the emergence of a new component, we can assume that the source may have been in an outburst phase, so this lower limit for the Doppler factor is probably an overestimate. So, in light of the above, further high-resolution VI observations are needed. And now about my other achievement. I presented these results at the Faculty Scientific Student Conference, where I got honored first prize. Later at the national conference, here I received the special award. Moreover, I earned the outstanding student award at the faculty last year, and this year I'm a recipient of the National Higher Education Scholarship. Furthermore, I have also presented at and participated in several conferences. Here I would like to highlight the Jive VIBL school, where I gained valuable experience in data calibration and learned how to use
Igen.
To illustrate this, here is an image which was processed by me using Casa. I have also been involved in science communication. This last one is actually outdated since yesterday, because now I am actually work there. Yesterday was my final exam here as a astronomer. So I'm going to master the astronomical image processing system for fringe fitting and calibration, and then I'm going to process multi blazar J14. Thank you for the attention.
Stop it.
I just have a comment that David forgot to mention that the data set he calibrated was a very fresh observation, observed the day before. So it was a very difficult one to handle, but he was very experienced. So I'm very proud of him to solve this problem.
At which redshift can you find this blazar? You said it,
It is around redshift 3, a bit more, 3.01, I guess.
But you can find those at redshift 6 point something.
Yeah.
Okay, if there is no more question, we will have a break and we will meet here at 12:50, and you can find some snacks outside too. So, thank you.